Ah, dang it. All right, let me go back to what we're doing today. Okay, so here's the agenda for today. We're going to do a lecture on upper air, and then they'll talk a little bit about balloon launches and how they collect that data. And then really the main part of this is you guys understanding the different Skew T diagrams. And I'll show you a couple. And then I'll show you all. Okay, quit doing that, whoever's doing that. And then I'll show you also Dr. John Meese, ice storms, so which we went through on Friday, which I thought we got pretty good freezing rain that day. Okay, so our learning targets is you guys should be able to describe the path of an air parcel, and then also identify the different parts of a Skew T diagram. Our connections to past lessons that you'll have to have a little bit of understanding of is air density. Remember, warm air rises, cold air sinks. The different layers of the atmosphere. You guys know that as we go higher in the troposphere, the temperature drops. So that's going to play a role because you'll see parts where the temperature actually rises. The lapse rate is the cooling rate of an air parcel as it rises, and then an understanding of temperature and dew point. Okay, so here is the presentation on upper air. Okay, when we talk about the upper atmosphere, we talk about the Earth's atmosphere about 5,000 feet. And you guys have looked at that stuff when I showed you the different ridges and troughs and how it's lower and colder air and higher and warmer air. So that's really what we're looking at when we launch those balloons to collect data from the upper atmosphere. The upper air is where we get our rain and drought, wind and calm, heat and cold at the Earth's surface. And then our forecasts, especially predicting into the future, come from the upper air patterns. So remember this fall, again, when I showed you those ridges and troughs and the upper air disturbances and the different low and high pressure, it shows us where those systems are moving. Okay, so if you look at this map right here and just type this into the chat, you guys, type in the chat what part of the United States you would have a ridge. Just type what part of the United States from looking at this, from looking at these patterns right here. Type in what part of the US you would have a ridge. And then there's actually two troughs. So you can type in what part you would have a trough also. So again, just type into the chat what part of the United States you would have a ridge and what part you would have a trough. Remember the ridge is where the air is rising. The trough is where the air is sinking. So I'll help you out with the ridge. See if you can finish that. There, see if you can finish that. That's the ridge. That's the ridge. All right, good job, Anna. Kristen, good job. Corbin, good job. Okay, so listen, when we go back to this here, the ridge is in the Rocky Mountain State, and then the trough in the east and the trough in the west. So a little review from this fall. Okay, so here's the second part of the lecture that you'll have to understand, and that's the parcel theory. And really just understanding the parcel theory, there's a lot of terminology here, a lot of wording in these PowerPoints, but just understand that according to the parcel theory, that if a parcel of air is warmer than the air around it, it will continue to rise. And that summarizes all of this right here. If a parcel of air is warmer than the air around it, it will continue to rise. Rising air is more unstable than non-rising air. In other words, the longer the air can rise, the more likely we have weather occurring because the air can continue to cool and form clouds. All right, just know that warm air is less dense than cold air, so the warm air rises, but also understand the lapse rate. As it rises, it cools. If it doesn't cool as fast as the air around it, it continues to rise. We call pockets of air air parcels because the parcel is a bubble of air that doesn't really have any definite size, but we assume it retains its shape and characteristics as it rises and sinks in the atmosphere. Okay, so here's what's happening all the time with the air around us. Warmer, less dense air is rising, and the cooler, more dense air is sinking and actually taking the place of the warmer air rising. If you continue to have the warm air rising, or you guys know a little bit about fronts, a cold front pushing that warm air even quicker, that causes an unstable atmosphere. So the warm air rising and cooling condenses, forming clouds. If it happens faster, like a front coming in, that causes more severe weather. Okay, so here's a diagram that shows the air parcel rising and the difference between stable and unstable. You can see the air parcel is 30 degrees Celsius at the surface. As it rises, it cools. Remember, rising air cools, that's the lapse rate. And it cools at a certain, about 5.5 degrees Fahrenheit every 1,000 feet. If the air around that parcel is warmer than the parcel, the air can't rise anymore, so it becomes stable. If the air around the parcel is cooler than the parcel, so the air rising continues to rise, then the air is unstable because that air can still rise. So again, when we talk about an air parcel and stable and unstable, just know, to make it simple, if the air is able to continue to rise or get higher, then that's an unstable area. If the air is able to stop rising or starts to sink again, that becomes more stable. Remember, sinking air is higher pressure, and high pressure, just to review, is usually a nice day because the air is not able to rise. Rising air is low pressure, and remember the cloud bottle. Remember the cloud bottle, when you let go of it, that was low pressure, the cloud formed. So that's what's happening here. In low pressure, the air is able to rise, and it will continue to rise as long as it's warmer than the air around it, or warmer than the air above it. I guess that's a better thing to say. Warmer than the air above it. So if you look at this right here, this 19 degrees Celsius is warmer than the 10 degrees above it. So it'll continue to rise. Okay, so stability and instability is based on the vertical temperature, the profile in the atmosphere. And you're going to see on these Skew T diagrams where the air is actually warms up a little bit as you go higher, and that's called a temperature inversion. A little bit of chemistry here. There's two different types of air parcels. There's an unsaturated air parcel, which means that the temperature and the dew point haven't been reached. And there's also a saturated parcel, which means that it has 100% relative humidity. So all this is saying is that the saturated parcel, the one that has more water in it, cools at a slower rate. And here's where the chemistry comes in. When things condense, when water vapor condense, That's an exothermic reaction. So that actually releases heat into the atmosphere. So when snow forms, or the water condenses, that's actually freezing is an exothermic reaction also. So that actually releases heat into the atmosphere. So sometimes that warms the atmosphere up a little bit more because of that process of condensing and freezing. Okay, so the reason that we look at these air parcels is to help us look at how stable or unstable the atmosphere is. And when we get into spring, actually, you guys won't be in here, but some of you might still read the National Weather Service discussions. When thunderstorms are going to affect us here in this area, they'll talk about a juicy, unstable atmosphere. And that's because that warmer air is able to keep rising at a faster rate. The lapse rate, or the rate at which a parcel of air cools, again, is about 5.5 degrees per 1,000 feet. So if you go up to the mountains for ski club, it is cooler in the mountains because you're higher up in elevation. In fact, if you go 10,000 feet up, it's about 55 degrees cooler than at the surface or 10,000 feet down. If the temperature, we showed you this in the diagrams that I showed you, just know that the temperature of the rising parcel, if it's cooler than the air around it, it starts to be pulled back down to the earth. That's called a stable atmosphere. And if the temperature of the parcel is warmer than the air around it, it'll continue to rise. Rising air creates an unstable atmosphere. Okay, so here's the next part of the lecture. So really what I want you to get from that air parcel theory is just know that a warmer air parcel continues to rise and it causes an unstable atmosphere. The next part is just how they take those measurements. They do those through radiosondes and weather balloon launches. So a radiosonde is just an instrument that's attached to a balloon. Those balloons are filled with hydrogen or helium, and it's carried up into the atmosphere. I think I showed you guys a video of a weather balloon launch earlier this semester. But when they launch those radiosondes, that balloon continues to rise in the atmosphere until it expands enough and pops. And then the radiosonde falls back to Earth. And remember, I said if anyone finds a radiosonde, automatic A for the class if you bring it back in. Those radiosondes or the instruments they launch, they usually have a little note on them that says return to the National Weather Service if found. So sometimes they do get caught in the jet stream and they sit and then they travel a pretty good distance before falling back to the earth. So those radiosonde sensors are linked to a radio transmitter and it sends information to a ground receiver. And what it does is it just gives us different data at different levels of the atmosphere. And again, a little review, remember 1,000 millibars is about ground level, 200 millibars or 250 millibars is where the jet stream is. So about 30,000 feet up or 35,000 feet up. And I believe those radiosondes or those weather balloons can travel to about 100,000 feet up. I thought that's what I remember reading. So here's a couple of images of how they launch the balloons. They blow them up 2 times a day, usually around 6 a.m. and 6 p.m. or 0Z and 12Z if you're going back to Zulu time. And launch them just like this. They have a little instrument attached to it. As it rises up in the atmosphere, it sends the data back to a computer and it gives us what we call the Skew T diagram, or data at different levels of the atmosphere. Okay, so yeah, here's the radiosonde flight. It can last about 2 hours. During this time, it can get up to about 115,000 feet and drift more than 125 miles. So you might find a radiosonde from a different part of the country. During the flight, the radiosonde experiences temperatures as cold as minus 130 degrees Fahrenheit and very low air pressure. And then once the balloon expands, because remember, as it goes higher, there's less pressure up there. So the balloon will continue to expand. Once it continues to expand, it'll eventually blow up or burst. And then that radiosonde falls back to Earth with a little parachute. So here's where those different weather balloon launches are located. You can see all around the world. And what that does is it gives us data to all different parts of the globe. And we use that data to predict the weather and our location. Okay, so here's how that data is used. They input the numbers into weather prediction models. Remember, all the models that we look at are based on math. So they put in dew point, temperature, wind speed, and direction at different levels. And then those weather models, the ones that you guys actually use, those are used to predict the weather based on the upper air. It's used to make predictions for severe storm or flight forecast, and also ocean or marine forecast. When I flew last week over Christmas break, because I don't like flying that much, I always look at the National Weather Service aviation website, because that shows me, or that tells me, where the turbulence is going to be on the flight. Also, I knew I was flying into freezing rain, so I looked at the upper air data for Grand Rapids International Airport, Gerald R. Ford, because, again, I don't like flying, and any little type of bump worries me a little bit. So I do look at that, and they use those weather balloon models for the aviation forecast. It's used for weather and climate change research. We can make predictions for the month of January now, if it's going to be warmer or cooler than average. And then also for pollution research and satellite data. Okay, so here's the last part. The data from these is plotted on a Skew T diagram. And the reason it's called a Skew T diagram is because the temperature lines are at a diagonal upward movement. I'll show you what I mean by that. Okay, so here's a Skew T diagram. So these are, if you can see this on your screen, and we'll look at this when you guys come back next week also, but these diagonal lines are the temperature lines. And that's why it's called the Skew T. These are skewed, or these are temperature lines that go up at a diagonal, these brown lines. As you go higher up here, this is the atmosphere. So let me show you one that might be a little, here's one that's a little more clear. And really, these are the only two lines, you guys, that you guys will have to identify. The temperature line and the dew point line. So the temperature line here is red, the dew point is blue. The closer they are together, the more saturated the air. And then also identify where these inversions occur. Remember, in the troposphere, the temperature drops with height. So going up on this diagram, this is going up in the atmosphere. This is a ground level down here. This is near the top of the atmosphere. So temperature is supposed to drop in the troposphere. Every now and then it rises a little bit. That's called the temperature inversion. Okay, so again, the only two lines that I want you guys to identify here, or recognize, I guess is a better word, is temperature and the dew point line. And then we'll talk about other things such as the CAPE, which is more for severe thunderstorm weather, and wind speed and direction and all that, when you guys are actually back here and you can see this a little bit better on my screen. So across the country, these radiosondes provide these different data maps that you look at, and I'm going to show you a couple different ones that you should be able to easily identify on a test. Okay, so here's a couple right here. Here's your freezing line. This is Celsius. So this is a little bit easier to see, actually, the temperature lines, how they're a diagonal line. So your snow Skew T diagram has all of the saturation below the freezing line. And when it hits the ground, it's still below freezing. So that gives us snowflakes. Here was from the other day. Notice part of the saturation line where temperature and dew point are the same is above freezing. So if those snowflakes, and snowflakes usually form best between -10 and -20, if those snowflakes fall into a warm sector of air, they melt, and then they freeze again when they hit the ground. So that was the freezing rain we got last week. So here's the easiest way to identify this freezing rain here is to just see a little nose, and that's how I identify it. This Skew T diagram has a nose here, and that's because the snow, the frozen precip, is able to melt while falling towards the ground. Able to melt while falling to the ground, and then freeze again, either when it hits the ground or right before it hits the ground. And then again, here's the snow one. Okay, notice everything is below freezing here. As it hits the ground, it's below freezing. Okay, so listen. This is pretty good right here. I'm going to show you this. So when you, some of you guys may have done this just by accident, but when you click on different parts of the map, it actually gives you a Skew T diagram. So watch this, watch this. And this is what you'll have to do on a test, but it's pretty easy. Let's go out here. Someone type in the chat, when you look out to Washington and Oregon out here, do you think the air is saturated, which means moist, just by looking at the colors here? Or do you think it's unsaturated or drier? Someone type it in the chat. So out here in Washington and Oregon, where you have all these colors, do you think it's moist or dry? Good job, Kelly Campfield. Trinity Cal, good, good. Anna, good. All right, Carson, good job. Okay, so listen, when I click on this, here is your Skew T. Now, this is red and green. This is red and green, but notice how close these lines are all the way up. So if you said moist or saturated, actually use saturated. Remember, Miss Andre doesn't like the other word. When you see these lines connected like this or really close together, that means the air is very saturated. And it's saturated at a very high point. So this is easier to see the numbers. This is 1,000 millibars. All the way up is the upper parts of the atmosphere. You can see that it's connected at a very high point. So that means saturated or higher clouds. And then it dries out when you get up here. Now, here's the other thing. Temperature continues to drop with height. You can see the temperature down here at ground level is 50. At about 300 kilometers, the temperature, if I could read this line, but it's like -50. Now, look at this one. Look at this one. Let's go down to Phoenix. Anyone ever have been to Phoenix? Type it in the chart if you've been to Phoenix. Or Sedona, or the desert.
I have.
Good, good, Corbin. You look like a Phoenix guy to me. Okay. Okay, so, whoa, okay, type this into the chart, or say it. Is the air usually dry or wet in Phoenix?
Dry.
Yeah, it's dry. It's dry. So think of what you just looked at with how wet it was out here in the Pacific Northwest, and look at this Skew T. So what do you notice now about the lines on this Skew T? Are they connected or further apart?
Further apart.
Yeah, they're further apart. So if the dew point is not close to the temperature, it means drier air. So this is a Skew T from the desert Southwest. Much drier air, and actually they don't really connect at all. So probably a sunny day also. And you can see, hey, you can see here a little bit of a temperature inversion. So temperature rising and then dropping. Temperature rising right off the ground and then dropping. So here's just one more. Let's look at ours right here. Let's look at ours for today. Oh, this is a good one. Okay, what do you notice about near the ground? What do you notice about near the ground? Temperature and dew point are the same, which means saturated air or clouds forming. And if you look outside right now, we have low clouds. And then as you go higher up into the atmosphere, the air is dry. So right now, if you took off from Muskegon County Airport, you would have a low cloud deck. And then once you got above it, then it would be drier air up there and probably good flying. And you can see here also that the temperature does start to rise around 900 millibars. So that'd be a question on a test too. Where does the temperature inversion take place? And if you go over here, these are the millibars. So the temperature inversion takes place at about 900 millibars. And it lasts until about 850, and then it starts to drop again. And then I'll do one more, you guys. But if you go up to this snow system, actually, let's go to this freezing rain mix up in Vancouver. Spent a week there one night. Actually, I heard Vancouver is a pretty good town. Anyone ever been to Vancouver? Vancouver?
Spent a week there before.
Hey, here's Vancouver right here. And you can see this was in the snow sector. Notice the saturation is all below freezing. So all snow in Vancouver. So just to kind of paraphrase this, when we look at these Skew Ts, you should be able, let me click on another one. Let me click on another one and you can type it in. Okay, let's click on this one right here. Just tell me at the surface, this is a good one right here. At the surface, type it in, would the air be dry or not dry? Just type it in down here at the surface. Would you have, you could say more dry or less dry, or more dry or more wet. Yes, Odessa County. So again, if you're looking down here, because the dew point and temperature are not that close together, these two lines, it would be drier. Now, would you expect some clouds, some higher clouds? And yes, you would, because it becomes saturated as you get above 500 millibars. So that'd be higher clouds. So one last thing, you guys. One last thing. We can use those. Oh, why didn't you tell me I wasn't presenting anymore, you goofballs? I thought I stopped recording. I stopped